Totally non-negative matrices appear in many areas of mathematics. They appear wherever matrices appear. They appear in linear algebra, in differential equations, in probability, and they appear in graph theory. And the way that they appear in graph theory is really nice. So let's look at that. One source of totally non-negative matrices these come from, one way that they turn up is from the class of graphs known as planar networks. Let me show you an example first, and then we can do a careful definition. So for example, let's let G be the graph with vertices on the left, which I'll call S1, S2, S3, and S4, and vertices on the right that I'll call T1, T2, T3, and T4. And let's let all of the edges be oriented from left to right. Maybe it'll complicate the picture if I put in all the edges, but all edges are pointing that way. Let me define a matrix A, which depends on the graph G by Aij equals the number of paths. These are directed paths, we have to go with the arrows, from Si to Tj. This is called the path matrix of G. So in the example, A is, let's see, from 1 to 1 we have exactly one path. From 1 to 2, that is S1 to T2, exactly one path. From S1 to T3, exactly one. From S1 to T4, there's 0 paths because this path is directed from left to right, so we can't go back that way. 0. From S2 to T1, now all the paths go from left to right, so we can go above this region or below it to this vertex and then go to T1. So there's 2 options. Same thing with T2, because we can go below or above this region to get to that vertex, and then one way to T2. And same to T3. To go to T4, from T2 to T4, there's one way to do it. And then starting at S3, well, it's pretty much the same thing, because once we get to this vertex, it's just like we started at S2. So there'll be 2, 2, 2, and one way to get to T1, T2, T3, and T4. And if we start at S4, then we have to go above this region. We can get to T1 in one way. We can get to T2 in one way. We can get to T3 in one way, and we can get to T4 in one way. It turns out that this matrix is totally non-negative. I guess it's not too hard to see because the entries are all non-negative. The determinant is 0 because we have 2 columns that are equal. So now we just need to check 2 by 2 minors and 3 by 3 minors. So 3 by 3, I guess we can't use both of these columns. We can only use one. And we can't use both of these rows because theirs equal. So 3 by 3 minors. I guess there's only one if we can't use both of these rows and can't use both of those columns. There's just the determinant of 1, 1, 0, 2, 2, 1, 1, 1, 1. And that's 0 because we have 2 equal columns. Oh, we had 3 equal columns here. Alright, so then the 2 by 2 minors, I guess we can't use both of those columns. So there's only 3 2 by 2 minors. We've got determinant of 1, 0, 2, 1, or determinant of 1, 0, 1, 1, or determinant of 2, 1, 1, 1. 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 0 is 1. So those are all non-negative. Alright, now the natural question to ask is, which graphs like this are going to lead to matrices that are totally non-negative? Well, the answer is the planar network, so let me define that carefully. So which graphs have totally non-negative path matrices? So they have to be directed acyclic planar graphs. We'll call a directed acyclic planar graph a planar network of order n if it can be embedded in a disk in the plane so that n sources, that is vertices with in degree 0, S1 through Sn, and n sinks, those are vertices without degree 0, T1 through Tn, appear on the disk itself, or on the boundary, in clockwise order, or could be counterclockwise. S1 through Sn, Tn through T1. So if we look at our example again, we had the sources S1, S2, S3, S4, T4, T3, T2, T1 in clockwise order, 1 through 4 and 4 through 1. put up the definition of the path matrix again. So the entries are Aij, where Aij equals the number of paths from source I to sink J. I don't know why we call these sources and sinks. In England, they call them sources and targets, which is nice because source and target begin with 2 different letters. But I don't know, we call them sources and sinks. All right, one thing I want to observe before proving that the path matrix of a planar network is always totally non-negative is that in the determinant of A, which is a sum of sine of W, A1 W1 through AN WN, the term corresponding to W counts all path families from, let's say all path families, I'll give them a name. Pi equals pi 1 through pi n. Where the ith path, pi I, is a path from source I to sink WI. So each of those contributes. This is the number of families from source 1 to sink 1, source 2 to sink, source 1 to sink W1, and then A2 is source 2 to sink W2, etc., up to source N to sink WN. Let me write this a little bigger. Now, each such path family contributes to the determinant. Well, it'll contribute 1 to this product, and then it'll come up with a plus or a minus sign. So it contributes plus or minus to the determinant, I guess, in this term. In particular, it contributes whatever sign of W is. And I'll prove the result that these matrices are totally non-negative in 2 steps. So first theorem, let me look at just the determinant of A. So let's let A be the path matrix of planar network G of order n. Then the determinant of A equals number of non-intersecting path families pi 1 to pi n. Now they'll necessarily be type identity because we can't have any permutations other than the identity if none of the paths are allowed to touch. So it counts the number of non-intersecting path families pi 1 through pi n. So pi I is a path from source I to sink I. Alright, so to prove this, so let's let pi 1 through pi n be a family of n paths of type W in Sn. That is, so pi I goes from source I to sink Wi. So if the paths of W do not intersect, then pi contributes 1 to the first term of the determinant. So let's suppose pi has at least one pair of paths which share at least one vertex. And let's let I be the least indexed such that pi I and pi I plus 1 intersect. Now those two paths might intersect multiple times. Let's name the first index, the first vertex where they intersect, Z. So I guess pi contributes sine of pi to the determinant. Now let's consider another path family that's related to pi. Let's consider the path family, I'm going to call it pi prime, related to pi by pi prime I equals pi I up to z, and then pi I plus 1 after. And then pi prime I plus 1 equals pi I plus 1 up to z, and then pi I after. So we're swapping paths pi I and pi I plus 1 at z. So they're just like they were before z, and then they swap. So then pi prime is counted somewhere in the determinant, and it contributes sine of the type of pi prime, whatever that is. But the type of pi prime equals SI times the type of pi, because we swap those two paths. And that's SIW. So pi prime contributes sine of SIW, which is negative sine of W. So together, pi and pi prime contribute 0 to the determinant. Now the map pi to pi prime that we get by swapping the two paths is its own inverse, so it's an involution. So this partitions all intersecting path families into pairs that contribute 0 to the determinant. So that means the only path families whose contributions are not canceled out are the non-intersecting path families. So that's the end of that proof, and this result and the next corollary together are usually known as Lindstrom's lemma. They're due to Lindstrom in 71, and actually earlier, Carlin and McGregor in 59. So they say that for the path matrix of a planar network, not only is the determinant non-negative, but all the minors are non-negative. So let's let A be the path matrix of planar network G. Then the determinant of the IJ submatrix of A equals the number of non-intersecting path families from the sources indexed by I to the sinks indexed by J. And now that we've proved the first theorem, this follows very easily. And the reason this is true is that Aij itself is the path matrix of a smaller planar network. Let me call it Gij, which is G with all sources but I erased, and all sinks but J erased. So if we go back to our example, if we, let's say, erase source 2 and name them S1, S2, S3 this way, so we're forgetting about that. And then if we erase sink 4, then we can name the sinks are going to be T1, T2, T3 here. And then the path matrix of this new planar network is going to be, let's see, from source 1 to sink 1, 2, and 3 we have one path. From source 2 to sink 1, 2, and 3 we've got two paths. And from source 3 to sinks 1, 2, and 3 we've got one path. So this is a submatrix of the original path matrix. Now there's so much intersection in this graph that I don't think we can get a very interesting example. So let me put up a different graph so that we get maybe a better example. And I guess in this corollary, well, I said the determinant of every minor is equal to the number of somethings. The number of somethings is certainly non-negative. So let's add thus A is totally non-negative. So We just showed that every single minor of A is a non-negative number, so it's totally non-negative. All right, another example. Let's let G be this graph, and let's say all the edges go up and to the right. And let me put source 1 here and source 2 there, and then sink 1 here and sink 2 there. And the path matrix is, let's see, from source 1 to sink 1, these are all of the lattice paths of length 4 that have 2 steps up. So that's 4 choose 2, so there's 6 of those. From source 1 to sink 2, we've got 3 choose 1, so 3. From source 2 to sink 1, we've got 3 steps choose 1 up, so that's 3. And then from source 2 to sink 2, we've got under the square over the square 2. Now the determinant of A equals 12 minus 9, which is 3. So we should be able to find 3 families of non-intersecting paths that go from sources 1 and 2 to sinks 1 and 2. So let's see if we can do this. So we could go all the way to the right and up, and then that leaves the S2 to T2 path. Well, we've got 2 options. Go down here or go over. So those are 2 non-intersecting path families. And then if we take the bottom path family and go over and up and over and up, so over and up and over and up, then the top family can go up, the top path can go up and over, so that's a third path family. Let me draw these again in case they're not visible enough. So those are the 3 non-intersecting path families counted by this determinant being equal to 3. The end.